Now let's continue our discussion of time dilation with an example of how we can manipulate that. Suppose a cosmic ray, which we're going to show here as mu, colliding with a nucleus in the upper Earth's atmosphere produces a muon, which has a velocity v equals 0.95 c. So 0.95 c is the velocity of this muon particle, excuse me. And the muon then travels at constant velocity and lives a total of 1.52 microseconds, as measured in the muon's frame of reference. You can imagine this as a muon's eternal clock. How long does the muon live measured by an earthbound observer? Okay, so the proper time, so let me make this smaller so we can write about this. So the proper time here, delta t 0, is the frame of reference of the muon. And so that his time, as it's shown here, is going to be 1.52 times 10 to the minus 6 seconds. Okay? And his velocity is equal to 0.95 c. So just short of the expected velocity of light. Now we know that delta t, which is going to be this earthbound person here, his experience is going to be some correction gamma times delta t 0. And gamma, the formula for that was 1 over the square root of 1 minus v squared over c squared. So gamma is going to equal 1 over the square root of 1 minus 0.95 c squared over c squared. And so if you do this math here, you end up that gamma is going to equal 3.20. And if we put this back over here now, delta t is going to be 3.20 times 1.52 times 10 to the minus 6. So that delta t becomes 4.87 times 10 to the minus 6 seconds. So 3.2 times as long as the internal clock. So that's the effect of this velocity, and this is how much time dilation occurred. So in this situation, the muon lives much longer as the earthbound observer observing it compared to its own internal clock and observation. So let's look at something called the twin paradox. The twin paradox asks the question that if you have two twins that start out together and one twin stays on the Earth and the other twin gets on a rocket ship and spends, say, a year in the rocket ship traveling at some close to speed of light speed, when this twin returns, this twin is quite a bit younger than the twin that stayed home. So if we consider it in the frame of the earthbound twin, the earthbound twin would become old, but the astronaut twin would stay young. Now what each person, if you considered it from the earthbound twin's frame, the astronaut twin has been gone for a long time. But to the astronaut twin, they've only been gone for a year. who's correct? Well, they both are. And that's the paradox. The paradox is that they're both correct. And based on special relativity, one experiences the time dilation. So what is gamma if V is 0.065 C? And this is a pretty simple calculation. Gamma, again, is equal to 1 over the square root of 1 minus V squared over C squared, which is equal to 1 over the square root of 1 minus 0.65 C squared over C squared. So this is going to be 1 over the square root of 1 minus, and 0.65 squared is 0.4225 C squared over C squared. So this is going to be the square root of 0.5775. And the square root of this is 1.32. So gamma here is 1.32. Now let's take a look at this second problem. Suppose the twin experiment, the rocket travels at 0.8 C, so V is going to be 0.80 C, and takes 6 months to reach the star. So if we use the delta T0, the proper time, as the twin that's in the rocket, then we're saying that the total travel is one total year. And the twin goes from being 30 to 31 years old. And the question is how old is the other twin? So delta T, so gamma here is going to be 1 over the square root of 1 minus V squared over C squared. So this is going to be 1 over the square root of 1 minus 0.8 C squared over C squared, which is going to be 1 over the square root of 1 minus 0.64. And that's going to be the square root of 0.36. And the square root of this is 0.6. And so gamma is going to be 1 over 0.6. 1 over 0.6 means that gamma is 1.667. So delta T is going to be delta T0 times gamma, or delta T, or 1.00 times 1.667, or 1.667 years. So she will be 31, and her sister will be almost 32, 31.667. So even at a fairly high rate of speed, 6 times 0.8 of speed of light, the change, or the time dilation, is fairly small. It's not until you get into fairly high rates of speed that you end up dealing with that. Now let's talk about the second phenomenon. The first phenomenon was time dilation. The second phenomenon is length contraction. Now when you look at lengths, if you're all in the same frame of reference, it all looks the same. However, if you have two different observers and two different frames of reference, then the distances really are actually different. And proper length is the same as proper time in the fact that it's now the distance between 2 points measured by the observer that is at rest relative to both points. And that last point there is important, relative to both points. So we have two individuals here. The first individual is at rest. The second individual is moving at a velocity of v. So the earthbound observer sees a muon, again that particle, traveling a distance of 2.01 kilometers between two clouds. Now that would be L0 because he is at rest relative to the 2 points. The other individual is moving, and the distance now is only 0.627 kilometers. The Earth, the air, the clouds are all moving relative to the muon in its frame and all appear to have smaller lengths. Notice the clouds are smaller. The size of the platform that he's standing on is smaller. Everything is smaller. Everything has been contracted by the fact that he's now moving. So the length contraction is the shortening of the measured length of an observer moving relative to the observer's frame. And the calculation is very similar, except because it's now not dilation but contraction, it's divided by the gamma. Therefore, we have the formula as written here. It's L0 times 1 minus v squared over c squared, the square root of that quantity. Now suppose an astronaut, such as the twin that travels, is traveling so fast that gamma is equal to 30. Now that's extremely close to the speed of light, by the way. She travels from Earth to the nearest star system, Alpha Centauri, that's 4.3 light years away, as measured by the earthbound observer. Now the earthbound observer is the motionless observer, is the L0 observer. How far apart are the Earth and Alpha Centauri as measured by the astronaut? And in terms of c, what is her velocity relative to the Earth? You can neglect the motion of the Earth relative to the Sun. So let's take a look at how we would do this. We know that L0 is 4.300 light years. And we also know that gamma, they gave us gamma, that makes it a lot easier, is 30.00. What we don't know is L. Now the equation is that L is equal to L0, divided by gamma, which is 4.3 light years divided by 30. And that math means that we're going to have 0.1433 light years. So what was 4.3 light years to the earthbound observer turns out to be 0.1433 light years. So a tremendous contraction in length. Now the second part of this question is a little more complicated. Again, we know that gamma is equal to 30. And we have unknowns. We have v in terms of c. So v is what's not known, and it needs to be calculated in terms of c. We know that gamma is equal to 1 over the square root of 1 minus v squared over c squared. And since the unknown here is v, we can rearrange this and do the calculation. We know that 30 is 1 over the square root of 1 minus v squared over c squared. So that 900, that's squaring, is going to be 1 over 1 minus v squared over c squared. That took the square root sign out. And if we rearrange this yet again, we have 1 minus v squared over c squared. We brought this to the top. That's going to equal 1 over 900. And if we finally do the calculation here, or solve for v, take the squared out, we end up with 0.9994 C. So to get a gamma of 30, you have to be very, very close to the speed of light, as you can see right here. Now here's another situation that we can look at. This is a particle traveling in the Earth's atmosphere. It's traveling at a speed of 0.75 C. To the earthbound observer, the distance traveled is 2.5 kilometers. How far does the particle travel in the particle's frame of reference? Now I'm just going to set this up as opposed to doing all of the math for this, but it's pretty straightforward. Again, we know that L0 is 2.5 kilometers, and we know now that V is equal to 0.75 C. So gamma is going to equal 1 over square root of 1 minus V squared over C squared. So that gamma is going to equal 1 over the square root of 1 minus 0.75 C over C squared. This is going to be squared. And once we get the gamma from this calculation, which should be pretty straightforward, we can then put that gamma and say that L is equal to L0 divided by gamma. And when we do all that, and when you do that, you should get an answer of 1.65 kilometers. So notice the first one, there was a pretty significant change in the distance. This one, because the speed is quite a bit less than C, comparatively less, then the change in length is far less affected, but it's real.